So in this video, we're going to take a look at the relationships between variables and how we use correlational analysis in some of the more common research designs in kinesiology, sports science, and exercise science in general. We'll define the coefficients of correlation and determinations, and I'll go over how we use simple and multiple regression analysis to predict or estimate a dependent or response variable. So if you've taken undergraduate statistics or even high school statistics, probably one of the first statistical concepts that you were introduced to was the correlation. And we use correlational research to understand relationships between different characteristics of our sample or different variables that operationally define these characteristics, such as VO2 max, heart rate, body composition. We're looking at muscular strength and endurance, number of push-ups someone can do, vertical jump heights, and things like that. So the most commonly used metric of correlation, and this is a bivariate correlation, that's correlation between two variables, is a Pearson correlation. More specifically, the Pearson moment correlation coefficient, or the PMCC, and it is quantitatively assessed using this scale from -1 to +1, where a negative correlation indicates that there is an inverse relationship between the two variables, and a positive correlation simply means that as one variable increases, the other variable also increases here. And these are the strength of correlation on the scale that is typically considered. For example, perfect correlation is obviously 1 or -1. No correlation is 0, and somewhere in between those two ends of the spectrum is weak and strong, and that may vary on the context in which the correlational analysis is being performed. So as I mentioned, the Pearson product moment coefficient of correlation is sometimes known as the PMCC, or simply denoted by R. It is a measure of reliability, and it gives the researcher a measure of effect, like how meaningful and how big of an effect does one variable have over another. The one thing about correlation, and in a few minutes here I'm going to talk about regression, is that the analysis or the results from the analysis do not indicate cause and effect. Always put if you're taking notes right now, or you have copies of my slides, make sure you highlight this, that correlation does not equal causation, or regression does not indicate cause and effect. We know, give you an example, that there is a strong linear relationship between IQ and shoe size, but having a high IQ doesn't determine the size of your feet or the shoes that you ultimately wear. And although I like to think if you're smart, you'd be able to get a pair of Air Jordan 1s, but unfortunately, even though there may be a strong relationship between the two, one doesn't cause the effect of another. So I think many of you understand that correlation does not equal causation, and in order to establish a cause and effect relationship, it has to correlation analysis is only one part of an entire research design or study, where ultimately it's up to the researchers who are using these statistical analysis to determine whether or not there is a cause and effect happening. So back to correlation, to these linear relationships. Again, I have here XY scatter plots that you might have seen before, even in just your remedial math classes here. And so a positive linear relationship or positive correlation is given by here as one variable increases, the other variable also increases, and you can see here this is a linear line. Or in a negative correlation, or an inverse relationship, as variable x increases, variable y decreases. Over here on the bottom left is an example of an XY scatter plot in which, quite frankly, there is no relationship, or the correlation is either at 0 or close to 0. And then here on the bottom right is what's known as a curvy linear relationship. So we're not going to spend a whole lot of time on that particular type of relationship, because that involves quadratic equations, polynomials. Just know that even if the entire sample distribution or relationship between x and y shows this nice curvy linear, this is a smiley face, curvy linear relationship, if we were to take ranges within that distribution, then perhaps, for example, the early part of the XY scatter plot shows that it's a inverse relationship in the linear ascent, or if we look at the tail end of that, and so that is a positive linear relationship. Okay, so if we use a specific example here, I have here, it's just taken from the Research Methods book. This is the Thomas book, and they have an XY scatter plot in golf of the percentage of hits that are on the greens and the putts per round. You can see here this is a positive linear relationship, and the dots here, the green dots, represent the actual scores, and this line here is a regression. I'm going to talk about linear regression in a sec here, and that estimates what, for example, the putts per round would be for a given percent of greens hit for this sample. So this is just one example of how to at least initially look at the relationship between interested variables, both in the actual score, what's called the observed score, and the predicted line or regression line that is used to estimate y based off x. So ultimately, we want to know how much of the one variable can be explained by another variable. And we use what's known as the coefficient of determination, which really is just the square of the Pearson correlation, r squared. You know, if you read some of the research, this r squared is most typically used when describing relationships between the variables. And as I mentioned, it measures the variance that is common between two variables. So I have here an example of VO2 max. I know I don't have it labeled here, but this is just the total observed variance in VO2 max that's represented by this box. The area over here highlighted in blue is the percentage of that total observed variance that can be explained by, in this case, distance run. While here on the white area, this is the unexplained variance. That's 19% in this case that is unexplained, that we don't know where it's coming from. It could be error, it could be random noise, but we do know based on this particular example that VO2 max, the variance in VO2 max, can be explained. 81% of the total observed variance can be explained by distance run. So what does that actually mean? And I apologize, I had to adjust my mic there. I know it's somewhat abstract, and you're trying to wrap your head around like what exactly does shared variance mean. It just simply indicates that as one variable changes, it will also influence another variable. So for example, if you measure distance run and the person were able to increase their distance run after training, we know based on this shared variance of 81% that their VO2 max most likely has changed as well, because the variance in one variable, aka VO2 max, it can be explained by the other variable, aka distance run. In this case, 81%. That's a correlation of 0.90, so that's pretty high. And just physically speaking, or physiologically speaking, it makes sense that someone who can increase their distance run most likely can increase their, or most likely indicates that their VO2 max is also increased. So this is a measurement of effect size, a measurement of meaningfulness. So whenever we're doing a regression or correlation analysis, and the R squared is one of those metrics or statistics that's typically included as a result to show a measure of effect, to show the effect size. Another way you can visualize this is using Venn diagrams. I'm sure many of you are familiar with Venn diagrams. So here on the left, the diagram shows that the relationship, there is no relationship between A and B, the variables A and B, and this would indicate a coefficient of determination of 0. Whereas the Venn diagram on the right, and this, just this rough, a rough estimation of the variance that is shared by variables A and B. In this case is 50%, and that's highlighted in the area that's common between A and B, and it's highlighted in green there. Okay, so that is the coefficient of determination, or shared variance, percentage of shared variance between variables A and B. So as an extension of correlation, we will discuss here prediction or regression analysis, which takes the the relationship between variables, and more specifically, we're trying to predict one variable based on the variance of another variable. So this one variable, we'll call it y, and that would be the response or dependent variable, and we want to know the influence of either one independent variable or factor. Some people like to call that explanatory variable. That's called a simple correlation when you're looking at x, the influence of x on y, or you want to look at the influence of multiple variables, more than one x, more than one independent variable on that specific response variable. Okay. So if x and y are highly related, then x can predict y to some degree and vice versa. Again, this does not imply or suggest cause and effect. And the relationship takes, the form of a linear line here, which can be explained with y equals mx plus b. So the statistical method that's used to predict that equation is based on establishing what's called this regression or prediction equation, where y here is the dependent or response variable we're trying to predict. M here, as you know, is the slope, right, which is dependent on the change in x over the change, the change in y over the change in x. And then b, of course, is the y-intercept. Now, when predicting a variable y, based off of another variable, which is the independent variable, unless the correlation between the two is 1 or -1, there's going to be an error in measuring or estimating that dependent variable. So here, for example, I've got here on the x-axis body weight, on the y-axis is the number of pull-ups that a person can do. I've got here, just a sample of, say, 10 subjects, and I came up with a regression equation that's shown here by this line, that y here, number of pull-ups, can be estimated using someone's weight and this equation. So for example, a person who weighs 140 pounds is predicted or estimated to be able to do 4 pull-ups. That's the estimation, and this shows you, I'm sorry, I didn't say 4 pull-ups, 8 pull-ups. I'll go back to where that 4 comes from. So again, let me back up a little bit here. A person who weighs 140 pounds is predicted to be able to do 8 pull-ups. Now let's just say that subject 3's actual number of pull-ups I can do is 12. The error between the two, between the actual score and the predicted score, is obviously 4. And just imagine if I were to collect more subjects who weigh 140 pounds, and some of them will be above that predicted score of 8, some of them will be below that, and eventually you'll get a distribution of what's called error scores or residual scores. The average deviation of the scores from the predicted score, it can be measured with what's known as the standard error of estimation or standard error of estimate. It reflects the amount of uncertainty when predicting a score y based off x. And it's a theoretical construct because we really don't know what the true error is in the population unless we were to collect data on every single person in the population and measure the correlation between x and y. But there is a mathematical formula that can be used to estimate or to calculate the standard error of estimation, which is dependent on the standard deviation in y. Remember, y is the variable that we're trying to predict, multiplied by the product or the square root of 1 minus the coefficient of determination. So if I'm looking at another example here where we're trying to predict someone's percentage of body fat off a sum of skin folds, we collect the data on subjects with their skin folds as well as their true percentage of body fat using DEXA. So this is somewhat abstract because I don't have an actual regression equation. I just have here as a line, which obviously indicates that there is a positive relationship. And so someone with a particular sum of skin folds would be predicted to have a percentage of body fat. And if I were to collect data on all of those subjects or participants who have the same sum of skin folds, some of them will be over and some will be under that predicted percentage of body fat. And over a period of time, or over time in which we were collecting this sample of data, the distribution of these residual score would resemble a normal distribution curve. So the standard error of estimation provides us the probability that someone's actual score will fall between plus or minus 1 standard error estimate, that's 68%, or plus or minus 2 standard error estimate, that's 95%. Okay, so the best way, like everything that we do in statistics, to describe or better explain this concept of regression analysis is to use a simple example here. So I've got to say that a researcher believes that cholesterol level is influenced by the time spent watching Netflix. Why is that important? Well, I mean, in this day and age, people spend a lot of time binge watching and they're not doing a whole lot of physical activity, so subsequently their cholesterol level may increase, especially if they're, downing a burger and hot dogs and popcorn while they're watching, 7 seasons of Peaky Blinders or something. Anyway, you should watch it. That's a great show. Anyway, I don't watch that much Netflix, just FYI. Yeah, I kind of do. Anyway, I digress. So if we're looking at this relationship, what is the null hypothesis? Cholesterol and Netflix. Yeah, that there is no relationship between the time watching Netflix and cholesterol. What do you think? What do you believe? Well, I believe that there is. As I mentioned earlier, times watching Netflix may indicate a sedentary lifestyle, more of a sedentary lifestyle, and therefore may increase someone's cholesterol level and perhaps lead to a higher risk of a cardiovascular disease, obesity, etc., etc. So we're going to be using RStudio today to look at some sample hypothetical data on Netflix time or Netflix viewership time, as well as cholesterol. So let's dive right in. Okay, so now we're in RStudio, and I'd like to start off with a blank slate here, a little tabula rosa. And you can see here I only got 3 panels open. I've got the console, my global environment, and the working directory in which I will be running the regression here. So I know in previous videos I've used a markdown file. In this one, we're just doing some quick analysis. So I'm just going to use a script, a brand new R script. So I'm going to click here, new R script. It's going to load the blank script here and this top left panel. I want to make sure that I have the correct packages loaded, in this case tidyverse, and chances are if you did the previous assignments you already have tidyverse loaded onto your working environment or into your RStudio directory of packages. But it's always a good idea to load that library because we're going to be using some of the functions that are embedded into the tidyverse set of packages themselves. Now we need to load the data set. We're looking at Netflix and cholesterol. The original file is, I show you here, you can download this off Canvas. The original file is in SPSS format, not a big deal because RStudio will allow us to import any data set or any format. So you can see here, I can do Excel, I can do a CSV. In this case, an SAV file, if you haven't worked with SPSS before, is one of the original data set formats. So we'll go ahead and import that in. You could see here that column 2 includes the time in minutes spent watching Netflix. These are daily times, meaning subject number 1 here, participant number 1, watches Netflix 168 minutes a day. Gosh, that's a lot of time there. And here on the 3rd column is the cholesterol concentration in millimoles per liter. So I've got that loaded. The next thing I'm going to do is I'm going to assign that data set to this data variable that I named CHL, right? It's short for cholesterol. Let's see. So I'm going to load that in. I'm going to go read dot. Let's see. This is SPSS format, so I'm going to put. Actually, no, it's underscore SPSS, and this one is called Netflix. Sorry, linear regression. There we go. And it is SAV. Oh, and this needs to be, sorry, in quotes. Now, another way you can do this, this is a bit of an aside. Notice I just put the name of the dataset, the file name of the dataset. And that's because it's already loaded into my working environment. But if you knew the absolute path in your your computer on where it's at, like say you saved it somewhere else, or you keep all your schoolwork or your coursework, then as long as you enter the exact path of where that is, you can load that into RStudio here. Okay, cool. So great thing about this is I can highlight this 3 lines of code, really just 2 lines of code, and I can run that. So I'll run the current selection, and notice it gave me an error here, which is fine because we did not, I should say, I did not name it correctly. Notice here, remember, RStudio is very picky about case and exact characters in a file name. I put underscore where I should have used hyphen. There, hyphen. I'm going to run this set of code, lines 1 through 3, run again. Cool. Oh, and gosh, I can't spell today. Library. I'm sure many of you have seen that already. Hit run. There we go. Cool. You know, I actually like to leave these errors, these mistakes, so you can see how I troubleshoot and correct them. So, gosh, I wrote 2 lines of code. I made like 3 mistakes already. So anyway, I've loaded the tidyverse package. I've loaded the data into this CHO data frame. So we are going to perform a linear regression. So I'm going to assign another data frame with what we're trying to predict. I'll show you what this means in a sec here. So cholesterol tilde, we're going to use time Netflix. Now, I already knew the names of the variables in this data set, but if you want to just do a quick check on the exact file names, or I'm sorry, the exact variable names, come down here to the console, type in names and CHO, that's the name of the data set, hit enter, and then you'll see case number, time underscore Netflix, and cholesterol. So if we come in here, line 5 says that I want to assign the Y variable. This means Y, or the variable in which we're trying to predict, that's the response variable, is cholesterol, by time Netflix, which is the independent variable, or the X that we're trying to use as a predictor for cholesterol. Cool. Then we're going to perform the actual linear regression. I'm just going to call it R. Remember, these are just names. These are just data names, so you can name it whatever you want. And for linear regression in RStudio, and actually in a few minutes here I'll talk about multiple regression, we use the LM function. LM means linear model. That means I am going to perform a linear model analysis on R naught. Oops, R naught 0. There we go. From the dataset CHO. Cool. So, then I will type in summary to display the summary statistics of that linear model. Go ahead and click on this, or highlight these lines, click on run. Go down here to the console, and these are the results of the linear regression. Okay, let's take a quick look at the results here. I know there's a few numbers that could be a bit confusing at first, but this is the result of the linear regression that we just ran in RStudio. What we're interested in, the main one here, is the coefficients. So those are the coefficients for the linear equation, regression equation. This is the R squared. Remember, that's the coefficient of determination. That is the percentage of the variance that is shared by, in this case, cholesterol and time on Netflix. The adjusted R squared just takes into account any random noise that are introduced. In the case of linear regression, a simple regression, we're only predicting one variable off another variable. Typically, the unadjusted R squared is used. The adjusted R squared is typically used for multiple independent variables. And the last one you should look at is the p-value, which as shown here is less than 0.000. So the null hypothesis that there is no relationship can be rejected because there is a less than 1% probability of observing a result, in this case of 15%, that's the shared variance, if the null hypothesis in the population were true, that there was no relationship between cholesterol and time Netflix. This means that we can estimate cholesterol based on someone's time spent on Netflix using this equation. And again, r squared is 0.151. That's 15.1%. That's common between the two, in variance between the two variables, between cholesterol and time Netflix, and it is statistically significant. The standard error of estimation is given by, gosh, I've missed that one here. Highlighted right here. So that's their standard error. So that's 0.53, roughly 0.538. So the error in estimating cholesterol from time Netflix in this sample is 0.538. Very important. Come back to that in a sec here. Now let's go ahead and generate a plot. Let's do an XY plot of this variable. So it's one thing to look at these results, but it's also good to look at how it looks in an XY scatter plot. Okay, so let's go ahead and generate that scatter plot in RStudio, and we're going to be using ggplot. I'm just going to put here generate XY plot of cholesterol from time Netflix. This little tilde symbol here in RStudio, that syntax means that y, if you want to remind yourself, y being predicted by x, or y as a function of x. Okay, so we're using ggplot. We will be using the CHO data set, the aesthetic. The x-axis will be time Netflix. Y-axis will be cholesterol. And we are going to be using a scatter plot, which in RStudio is known as point. Basically a bunch of XY points. Cool, so let's generate this plot first before I go into the regression part. I'm going to hit run. And over here on the bottom panel, you'll see the plot. So this is the XY plot for time Netflix versus cholesterol. As you can see, it's somewhat scattered all over the place. Now I want to fit the regression line to that plot. So I'm going to go ahead and add that in RStudio, which with the ggplot is known as smooth. The method we're going to be using is linear, so that's LM, linear model. And let's see, what else could I add here? Let's do no standard error. Put that as false. That just means I don't want to show the standard error bandwidth in there. And let's see the color. Let's do, I don't know, blue. I like blue. You're my dog, Blue. All right, so let me highlight that, hit run. There we go. So that is a scatter plot for time Netflix versus cholesterol, as well as the fitted regression line. So let's dig a little bit deeper into this scatter plot and see how we can interpret the data. Okay, so let's take a look at the results here. I've got here the XY scatter plot that we generated in RStudio. X-axis again is time spent on Netflix. Y-axis represents the estimated cholesterol concentration. The black dots here are the actual cholesterol level for the given time spent on Netflix, and the blue line represents the regression line that is defined by that equation that we outputted just a few minutes ago. So let's say, for example, that we wanted to estimate the cholesterol concentration for someone who spends 170 minutes on average on a daily basis on Netflix, which is a lot of binge watching there, right? So I'm going to write down here time is 170, and according to this regression equation, cholesterol level would equal negative 2.13 plus 0.044, multiply that by 170 minutes on Netflix. Enter all the numbers that punch that into your calculator. You should get roughly 5.35 millimoles per liter. Okay, so that's the estimated cholesterol concentration for a person who spends 170 minutes on Netflix. But look at the graph there. Look at just at 170 minutes in the x-axis there. There are people in this sample who have actual cholesterol concentrations above that estimated concentration of 5.35, and some of them are below that. So as I mentioned earlier, there is an error in estimating, in this case, cholesterol concentration based on our x variable, which is time Netflix. And that error or uncertainty is given by the standard error of estimation, which our studio found was 0.538. So given what we know, our next question for you is, what is the probability that an interval between 4.28 and 6.47 millimoles per liter would include this person's actual cholesterol concentration? So give it a shot. Okay, so to answer that question, 4.28 and 6.47, that's pretty detailed, right? You have to go back to what I talked about with the standard error of estimation. You treat the standard error of estimation much like any standard deviation, and the distribution of these error scores, oops, that's supposed to be a straight line, represents resembles a normal distribution. So here in the middle is the estimated or predicted cholesterol level. One standard error of estimation above it and below it represents 68% of the error scores in that distribution for a person that weighs, or I'm sorry, a person that spends 170 minutes on Netflix, and 95% falls between plus or minus 2 standard error of estimation. Now, the standard error of estimation, as we found out earlier, was or is 0.538. The predicted cholesterol level for a person who spends 170 minutes on Netflix is 5.35. I think you're just looking at it that 5.35, we're looking at the 95% interval. That's supposed to be plus or minus 0.538. So that means the lower 2 standard error. That's 2 standard error of estimation. That should be a 2. Remember, 2 standard error of estimation, 2 standard errors of estimation from the predicted value represents 95% of the distribution in the score. So minus 2 SEE is roughly 4.28 plus 2 SEE is roughly 6.47. That is the 95% confidence interval for these residual scores, or for these error scores. So therefore, there is a 95% probability that the interval between 4.28 and 6.47 would include a person's actual concentration, cholesterol concentration, who spends 170 minutes on Netflix. That's how you make that interpretation. So in that previous example, we looked at the influence of one variable has on another variable. We found that only 15% of the variance in cholesterol concentration can be explained by time spent on Netflix, which makes sense, right? We know that cholesterol concentration depends on someone's diet, their daily physical activity, their age, their sex, etc., etc. And the way that we could measure the effect of multiple factors on one response variable is is using what's known as a multiple regression analysis, which correlates more than one predictor or explanatory variables with a response variable, with our dependent variables. So let's take, for example, knee valgus torque, which is a biomechanical indicator of ACL injury risk. And we know that it is dependent not only on sex, but also on sprint time, age, jump power, vertical jump heights, etc., etc. So we use a multiple regression analysis to determine the best combination that predicts or estimates knee valgus torque. Now, I'm not going to spend a whole lot of time on the different methods of multiple regression, but one of the more common methods is what's known as a stepwise regression analysis, which combines a forward selection of predictors as well as a backward selection and determines the best combination that predicts the response variable. In this case, it could be knee valgus torque or cholesterol concentration. There are a number of different ways to extract these predictors, but we're going to use, in this case, a stepwise multiple regression. And so the equation, the multiple regression equation, is not that different from what I showed you in the linear regression. It's still linear, except this time there are multiple factors here, x1, x2, and xi, that are multiplied by the regression coefficients that are provided here by b1, b2, etc., etc. bi, and a here represents the intercept. So it's still linear, and the multiple regression then provides the intercept and coefficients that best predicts y, our response variable. Now, I should note there are a few problems associated with performing and using a multiple regression analysis. One is called shrinkage. This is in a case where the multiple regression model that we use in one sample may not fit on another sample. In fact, the model fit may actually shrink. So that goes in line with the specificity of the population in which we're trying to measure these multiple effects on a response variable. Another one is highly sensitive to sample size. And so depending on this, the number of participants in our sample will ultimately determine the amount of error that is introduced to the regression model. Also, having too many predictors, having too many factors or variables introduced into the model can also increase the proportion of variance or fit that is due to noise, that is unexplained. So, and like anything that we do in statistics, we like to keep things simple. We use a rule that the model, in this case the regression model, that uses the fewest number of predictors is the best one to use. It's most efficient. Cool. All right, so like anything, let's use an example to describe how we implement and interpret a regression and multiple regression analysis. So I'm going to use here a study that was conducted by one of my honor students a few years ago. She's now a graduate student. I shouldn't say a few years, this is just a year ago. And she looked at bat speed, and more specifically looking at the influence of specific biomechanical variables in predicting bat speed in a sample of 10 collegiate baseball players. So the response or dependent variable is the bat speed. The predictors that were considered in this regression was bat angular speed, X factor, which is hip-shoulder separation, stride length, vertical ground reaction force for the lead and backside legs, pelvic velocity, and trunk velocity. So that's a total of 7 predictors that are considered for this multiple regression. Each one of those players came into our biomechanics lab, and they all swung off and hit a ball off a tee. So that allowed us to measure the whole body kinematic, kinetic, and ground reaction force data during the swing. We then entered all of this data into our statistical analysis, and I'm going to show you how to perform a multiple regression in our studio. Okay, so let's go back into RStudio, and I've already made an R Markdown file that specifically looks at this multiple regression analysis in bat speed. And if you're taking my research methods course, KIN 6005, the sample data set that we're using for this regression as well as the Markdown file is available on Canvas. So if you want to follow along, you can go ahead and download that and run this analysis. So first thing I'm going to do is load that data set. In this case, it's called bat speed. I'm going to import that data set here. It's a CSV file. Hit import. It's previewing it, showing everything good. So I'll import that in here. And then I'm going to go into my RMD or Markdown file. I'm going to go ahead and knit it just so I can show you how it looks in a clean HTML page. So it's going to do its thing. I'll double check, make sure that there are no errors. I apologize if you run any errors. If you do, hit me up. We'll go ahead and fix it. Okay, so I just sped up to the knitted file here so you're not there waiting. For whatever reason, that took a while. Okay, so this combines a linear, this Markdown file combines a linear as well as, I'm sorry, let me back up. It involves a simple regression as well as a multiple regression. The simple regression here, I was just looking at the regression between angular speed and bat speed. As shown here, this is the XY plot between the two. If you're following along, you can go ahead and try this out in RStudio. Right here, this chunk of code is the linear regression in predicting bat speed from bat angular speed. This is the resulting equation, regression equation, y-intercept 7.4, and the coefficient for bat angular speed to predict bat speed. So I'm gonna go ahead and go down to the multiple regression, and then I'm gonna go back. I just want to show this to you, and then I'm gonna go back to RStudio and show you how it runs. So this is the linear model that we're using for the multiple regression to predict bat speed based on those 7 predictors or explanatory variables that I described to you earlier. And these are the results. So I'm gonna go back in here. This is multiple regression. That is line, which one was it? Nope, that's the linear regression. That'd be line 85 if you're following along. So let me show you what this is. What I did here is I assigned a data variable rfit with the linear model that is providing the regression, the multiple regression analysis. So we're trying to predict bat speed based off, that's that tilde, stance length, x factor, bat angular speed, pelvic velocity, trunk velocity, these are angular velocities, the ground reaction force, vertical ground reaction force on the lead leg as well as on the back leg from this data set. This is the bat speed data set. Okay, so we run that. And down here, summary, that just basically means show the summary statistics for this regression model. So I'm going to hit play or run this current chunk. And these are the results. Okay, so as I mentioned, when you run that line of code, you run the linear model, that's LM, that's what we're using to perform a multiple regression on bat speed, to predict bat speed based on stance length, x factor, bat angular speed, pelvis and trunk angular speed, the ground reaction force, vertical ground reaction force on the lead and backside of the bat. The BAT here, BAT, is the name of the data set that we're using. We run a summary, and this is what it provides in terms of the output in RStudio. This residuals here represent the error in predicting bat speed using these predictors, using these explanatory variables. So the residuals is the difference between the predicted bat speed and their actual bat speed for each one of the 10 players in our sample. Remember, these are a sample of 10 collegiate players. The one thing that you want to look at is this first column here. This first column lists the coefficients for the regression equation. So the y-intercept is negative 9.88, and then that is followed by the respective regression coefficients for each one of the predictor variable. The next one here, this column, is basically the p-values. So these show those variables that significantly predict in this case bat speed, so it shows which one has a significant relationship with bat speed. In this case it would be X factor, which is the separation between hips and shoulders, bat angular speed, and bat angular speed, X factor, and sound. Like those three, the trunk velocity was listed at 0.06. So the null hypothesis and null effect is that there is no relationship between these variables and the bat speed. We can reject that null hypothesis because, I'm going to show you here, this p-value here down on the bottom right represents the probability of observing a model fit, in this case of 0.99. I'll go over that in a sec here. The probability of observing that effect given in the general population that none of these factors have any influence on bat speed is less than 1%. So we can reject that null hypothesis and conclude that the combination of all of these variables, these predictor variables, significantly influence bat speed. In fact, look at the adjusted R-squared here. Remember, R-squared represents the proportion of variance that can be explained by all these variables. In this case, 99%. Now, there's some, now I would say controversy, there might be some discussion here because I have a total of 7 predictors. As I mentioned earlier, those can actually contribute to the randomness or the variance, proportion of variance that's due to the randomness and noise. I'll go over that in a sec here, but for the most part, a good proportion of the variance in bat speed can be explained by these 7 factors. And if you were to write down this equation, you would take this first column and put down negative 9.88, multiply that by 0.405 times whatever stance length you find for that person, etc., etc., and you go from there. So as I mentioned earlier, one of the limitations of using a multiple regression is that the more predictor variables that you have in your model, the higher chance that the proportion of shared variance, that's the proportion of the variance in bat speed that can be explained by all these predictors, it tends to go up. Because the more factors that you have in there, the less likely is to be that the model is able to distinguish between what is true and what is unexplained, what is just randomness. So there's a principle in statistics that you try to keep it simple, right? And so the model that best predicts this, in this case bat speed, that has the fewest number of predictors, a number of independent variables, is usually the one to use. So if I were to redo this model, this regression model, multiple regression model, I would run a correlation analysis, and then I would find that these 3 variables highly predictive or had a significant relationship with bat speed, and so I would just use these 3 variables to predict bat speed and rewrite the equation. So in this case it would be stance leg, X factor, and bat angular speed.